In the annals of scientific discovery, few figures stand as tall as Galileo Galilei. His revolutionary ideas challenged centuries-old beliefs and laid the groundwork for modern physics. Galileo's observations with his newly invented telescope, revealing mountains on the Moon and moons orbiting Jupiter, shattered the prevailing Earth-centric view of the cosmos. But his contributions extended far beyond astronomy. Galileo's experiments with falling objects conducted from the Leaning Tower of Pisa led him to formulate the principle of equivalence. This principle states that all objects, regardless of their mass, fall at the same rate in a vacuum. This groundbreaking insight paved the way for a deeper understanding of gravity, later formalized by Isaac Newton. Galileo's work also laid the foundation for the concept of Galilean invariance, a cornerstone of classical physics. This principle asserts that the laws of physics remain the same for all observers, moving at a constant velocity relative to one another. In other words, the physical laws governing a game of billiards on a moving ship are identical to those on land, as long as the ship's motion is uniform. This concept, seemingly intuitive in everyday life, has profound implications for our understanding of motion and the universe. Galileo's legacy extends far beyond his individual discoveries. His emphasis on observation, experimentation, and mathematical reasoning ushered in a new era of scientific inquiry. He dared to challenge established dogma and to trust the evidence of his senses and instruments. His courageous pursuit of truth, despite facing opposition from powerful institutions, serves as an inspiration for scientists and thinkers to this day. Galileo's spirit of inquiry continues to drive our quest to unravel the mysteries of the cosmos. To grasp the essence of Galilean invariance, we must first understand the concept of inertial frames of reference. An inertial frame is essentially any environment where an object at rest stays at rest and an object in motion continues moving at a constant speed and direction unless acted upon by an external force. Imagine a train moving smoothly at a constant speed on a straight track. The train in this case constitutes an inertial frame. A passenger inside the train who throws a ball straight up will observe it landing back in their hand just as they would if they were standing still on the ground. This is because the train and the ball are both moving at the same constant velocity. Now, consider another observer standing on the ground watching the train pass by. From their perspective, the ball thrown inside the train follows a parabolic trajectory, a combination of its upward motion and the train's forward motion. However, despite the different observed paths, the same laws of physics, Newton's laws of motion, govern the ball's behavior in both frames of reference. This is the essence of Galilean invariance. The laws of physics are independent of the inertial frame from which they are observed. The concept of inertial frames and Galilean invariance simplifies our understanding of motion. It allows us to analyze physical phenomena from different perspectives without altering the underlying laws governing them. This principle is fundamental to classical mechanics and has been instrumental in our ability to describe and predict the motion of objects from projectiles to planets. However, as we shall see, the seemingly universal nature of Galilean invariance breaks down at extremely high speeds, leading to a paradigm shift in our understanding of space and time. The Galilean transformation provides a mathematical framework for relating observations made in different inertial frames. It allows us to convert the position, velocity, and time coordinates of an event as seen by one observer to the corresponding coordinates as seen by another observer moving at a constant velocity relative to the first. This transformation is based on the intuitive notion that time is absolute and universal. In other words, all observers, regardless of their relative motion, agree on the timing of events. Imagine two observers, one standing on the ground, observer A, and the other on a moving train, observer B. Observer A sees a bird flying with a certain velocity. To determine the bird's velocity as seen by observer B, we use the Galilean transformation. This transformation simply adds the velocity of the train to the bird's velocity as seen by observer A. This makes intuitive sense. If the train is moving forward and the bird is flying forward, the bird appears to be moving even faster from the perspective of observer B. The Galilean transformation, with its assumption of absolute time, works remarkably well for everyday phenomena and for speeds much slower than the speed of light. It allows us to seamlessly translate observations between different inertial frames, providing a consistent framework for classical physics. However, this seemingly unshakable principle faces a formidable challenge when confronted with the speed of light, a universal constant that refuses to be confined by the rules of Galilean transformations. In the late 19th century, physics encountered a profound enigma: the speed of light in a vacuum. Experiments consistently demonstrated that light travels at an astonishingly fast but constant speed, approximately 299,792,458 meters per second. This discovery, while groundbreaking, presented a fundamental challenge to the established laws of physics. According to Galilean transformations, the observed speed of light should vary depending on the observer's motion. If you are moving towards a source of light, the light should appear to be traveling faster than if you are moving away from it. However, experiments showed that this was not the case. The speed of light remained stubbornly constant, regardless of the observer's motion relative to the light source. This perplexing observation hinted at a fundamental flaw in the Galilean framework. The constancy of the speed of light implied that time itself was not absolute, as assumed by Galilean transformations. It suggested that time could be relative, flowing at different rates for observers moving at different speeds. This realization, a radical departure from classical physics, paved the way for a new understanding of space and time, one that would revolutionize our conception of the universe. The constancy of the speed of light, once a puzzling anomaly, became a cornerstone of modern physics, leading to the development of Einstein's theory of special relativity. Einstein's insight, special relativity. In 1905, Albert Einstein, a young patent clerk at the time, published his groundbreaking theory of special relativity. This theory, built on the foundation of the constant speed of light, challenged the very fabric of classical physics. Einstein's key insight was that time and space are not absolute but are interwoven into a four-dimensional continuum called spacetime. This continuum is not static but is warped and stretched by the presence of mass and energy. Special relativity asserts that the laws of physics are the same for all observers in uniform motion, just as in Galilean invariance. However, it introduces a crucial modification. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source. This seemingly simple postulate has profound implications. It means that time is not absolute, but is relative to the observer's frame of reference. Special relativity introduced a new set of transformations, known as Lorentz transformations, to replace the Galilean transformations. These transformations account for the constancy of the speed of light and lead to counterintuitive but experimentally verified phenomena such as time dilation and length contraction. Einstein's theory, once considered radical, has been rigorously tested and confirmed countless times, solidifying its place as one of the cornerstones of modern physics. Time dilation. Time is relative. One of the most startling consequences of special relativity is time dilation. This phenomenon implies that time is not an absolute, universally ticking clock, but is relative to the observer's reference frame. Time dilation states that time slows down for objects in motion relative to a stationary observer. The faster an object moves, the slower time passes for it compared to a stationary observer. Imagine a spaceship traveling at a significant fraction of the speed of light. An astronaut inside the spaceship experiences time passing normally, just as they would on Earth. However, for a stationary observer on Earth, time appears to be passing slower for the astronaut on the spaceship. This means that the astronaut would age slower than people on Earth. While the effects of time dilation are negligible at everyday speeds, they become increasingly significant as an object approaches the speed of light. This phenomenon has been experimentally verified using atomic clocks flown on airplanes and satellites, confirming the predictions of special relativity. Time dilation is not merely a theoretical curiosity, but has practical implications for technologies such as GPS satellites, which require precise timekeeping to function accurately. Length contraction. Space is relative. Another mind-bending consequence of special relativity is length contraction. This phenomenon dictates that the length of an object in motion appears shorter in the direction of its motion relative to a stationary observer. The faster an object moves, the more it appears to be contracted in the direction of its motion. Imagine a spaceship traveling at a significant fraction of the speed of light. For an observer on Earth, the spaceship appears shorter in length compared to its length at rest. This contraction occurs only in the direction of motion. The spaceship's height and width remain unchanged. Like time dilation, the effects of length contraction are negligible at everyday speeds, but become increasingly pronounced at speeds approaching the speed of light. This phenomenon, while counterintuitive, has been experimentally verified, further solidifying the validity of special relativity. Length contraction, along with time dilation, underscores the interconnectedness of space and time in Einstein's four-dimensional spacetime continuum. The breakdown of Galilean invariance. The advent of special relativity revealed the limitations of Galilean invariance. While this principle holds true for everyday phenomena and for speeds much slower than the speed of light, it breaks down at relativistic speeds. The assumption of absolute time, embedded within Galilean transformations, fails to account for the constancy of the speed of light. At relativistic speeds, the effects of time dilation and length contraction become significant, rendering Galilean transformations inaccurate. The relative nature of time and space, as revealed by special relativity, necessitates a new set of transformations. Lorentz transformations to accurately relate observations made in different inertial frames. The breakdown of Galilean invariance at relativistic speeds does not diminish its significance in classical physics. It remains a fundamental principle for understanding motion at everyday speeds, and continues to be instrumental in various fields, from engineering to astronomy. However, special relativity extends our understanding of motion to encompass the realm of extremely high speeds, revealing a universe far more complex and counterintuitive than previously imagined. Implications and applications. The principles of Galilean invariance and special relativity have profound implications for our understanding of the universe. They have reshaped our conceptions of space, time, and motion, leading to groundbreaking discoveries and technological advancements. Special relativity, in particular, has revolutionized fields such as cosmology, particle physics, and astrophysics. One of the most significant implications of special relativity is the equivalence of mass and energy, encapsulated in the famous equation EMC2. This equation reveals that mass can be converted into energy and vice versa, a concept that underpins nuclear energy and explains the energy source of stars. Special relativity also plays a crucial role in our understanding of the behavior of particles at extremely high speeds, such as those in particle accelerators. The principles of Galilean invariance and special relativity have also found practical applications in various technologies. GPS satellites, for example, rely on both principles to maintain accurate timekeeping and positioning. The satellite's motion relative to Earth causes time dilation, while their altitude above Earth results in a weaker gravitational field, causing time to run slightly faster. These effects must be carefully accounted for to ensure accurate GPS measurements. Conclusion: a legacy of discovery. The journey from Galilean invariance to special relativity is a testament to the power of scientific inquiry and the evolution of our understanding of the universe. Galileo's groundbreaking ideas laid the foundation for classical physics, while Einstein's revolutionary insights extended our grasp to the realm of relativistic speeds. These principles, while seemingly disparate, are interconnected, each revealing a facet of the grand tapestry of the cosmos. Galilean invariance, with its intuitive simplicity, continues to govern our everyday experiences and underpins various fields of study. Special relativity, with its mind-bending implications, has revolutionized our understanding of the universe, revealing the interconnectedness of space and time and the equivalence of mass and energy. The legacy of these principles extends far beyond their scientific contributions.